Hello, 8th graders. This is a video about specific heat. Specific heat is in our properties unit because it is a way for us to figure out what your mystery cylinder is at the end of the unit. So everything that I show you in this video is going to be applied to the lab in a couple of weeks. The idea that I want you to think about to help you to imagine what specific heat is this idea of a preheated oven. So if you preheat an oven to 350 degrees, everything inside of that oven gets to the same temperature. The air, the rack, and if you leave it in there long enough, the food that you put in there too. So the question becomes, when I open up that oven and all of the air rushes out and hits me in the face, that's some really hot air, but it doesn't burn me. However, if I reach into the oven and touch the rack or the food, that is definitely going to burn me. So the reason why that happens is because of this thing called specific heat. And we'll get back to the pizza and the oven thing in just a second, but I want you to be thinking about that idea as we go. So the first thing that I need you to put down on your notes is the biggest idea for specific heat there is, and it's the one that's at the top. Heat and temperature are not the same thing. So up until this point, you might have thought that a thermometer measures the amount of heat that's in something. It doesn't. Heat is a type of energy. Heat can make things temperature go up, but heat and temperature are not the same. So let me see if I can give you an example. Pretend that you had two different containers. There's the one on the left right here that has a lot of water in it, and the one that's on the right that has just a little bit of water. If I put them over the exact same heat source, so the exact same flames, they're both getting the same amount of heat going into them, which one is going to boil first? Well, hopefully you could say the smaller one, because you know that less water takes less time to boil. Well, the amount of heat that's going into these containers is the exact same amount of heat, but because there's so much more water on the left-hand side, it takes more heat to get the temperature to the same spot, 100 degrees. They're both going to get to boiling eventually. So more heat required on the left-hand side because there's more water in there. There's less heat required on the right-hand side because there's less water. Remember, we have to get those molecules to shake so violently that they rip apart from each other. That's what a phase change is. That's what boiling is. Well, because there are so many fewer molecules on the right, it's not going to take as much energy to get them all to shake. Way more on the left. So specific heat is a property, as I said. That means that if you have a particular kind of material, you can know something about that type of material that is true for all amounts of that material, because that's what a property is. So think of it like this. Pretend that you have 4 different types of material. We've got green material, orange material, blue, and yellow. These are all different materials. And we want to know what their specific heat is. The specific heat is the amount of heat that's required to get a single gram of that material to go up by a degree. So this green material, we have a gram of it. Whatever temperature it's at, we want it to go up 1 degree. Same with the orange and the other two. Well, specific heat tells you how much heat it takes to make those things go up. So pretend like green takes a whole bunch of heat. It takes 10 joules of heat to make that material go up a degree. This one, the orange one, maybe takes 6, all the way down to this yellow one. Maybe the yellow one doesn't take very much heat at all to make the temperature go up. They're all going to get to the same temperature, but they're going to carry different amounts of heat in them. So if we go back to the oven example with the pizza in it that we preheated, all of the different things inside of the oven are different materials. The gas, the air that's in there, the pizza itself, and of course the rack that's in the oven. Since they are all different materials, they all have different specific heats. It requires a different amount of heat to get them to the same temperature. So they're all at 350 degrees, but some of them required a lot more heat to get there than others. Well, the more heat they're carrying, the more able they are to burn me. So based on this example, I want you to pause the video and think to yourself, which material must have the highest specific heat, the air or the rack? And please unpause it when you have an idea in your mind. So hopefully you have an idea. Since the rack is the thing that's going to burn me, that would be like the green box, the thing that can hold a lot of heat when its temperature goes up. The air inside of the oven is a lot like the yellow box. It didn't take very much heat to get it to go up to the same temperature as the rack. So if I touch the air, it's not carrying very much energy. It's not going to burn me. It still is the same temperature though. However, the rack can hold more heat. And so if I touch it, there's going to be more heat that's going to come out into my hand if I touch it. So let's talk about how to calculate this. This looks like kind of a scary equation, but it's not so bad when you break it down. First thing I need you to do, we're on the next page of your notes. First thing I need you to do is label all of these things units. So I don't know why they picked a Q. I'm sure there's a reason out there, I just don't know what it is. But Q is the amount of heat that we're going to add to something. And we measure heat in joules. Temperature is, of course, going to be metric in this class. We're going to measure that in degrees Celsius. So when we add heat to something, its temperature is going to go up, or if we remove heat from something, its temperature will go down. We're going to measure the change in temperature. So that's what this triangle means, is change. So if my temperature goes up 10 degrees or up 25 degrees or whatever, that's what we're going to be looking at there. Mass, of course, is measured in grams. The last variable in this equation is C, and that's this thing that we call specific heat. If you were to rearrange all this, you would see that the units have to have joules, grams, and degrees in them. So they have kind of a funky unit for specific heat. It's called joules per grams degrees Celsius. And that unit sounds kind of crazy, but if you look at it closely, hopefully it'll make more sense. It's really saying like how much heat, how many joules does it take for every single gram to go up a degree Celsius? How much energy does it take to make a little bit of this material change its temperature? That's what this unit is telling us. Now let's talk about how this might actually work. So let's say that I took a piece of metal from the boiling water, just like you did in the lab, and I put it into my calorimeter and measured how much the water's temperature went up. How am I going to actually calculate the specific heat of that metal that I just dropped in the water? Well, first thing we need to know is the mass of our metal. Just throw it on the scale. We've got that answer right there. We also talked about in class that a single gram of water is a milliliter of water. So when you filled up your calorimeter, you used a graduated cylinder. Whatever you got from milliliters is the same as the grams. So now we have our mass of our water and our metal. We also need to know what they started at, what their starting temperatures were. So because our metal was coming out of boiling water is 100 degrees Celsius. So it's going to be 100 degrees Celsius just like the water it was in. The calorimeter water, though, we have a thermometer sticking out of it, and it's going to start at room temperature, so 20 degrees Celsius. It's nice and cool. Then we're going to put those two things together. We're going to take the really hot metal, put it in the water, and eventually they're going to equalize. They're going to come to the same temperature. The hot metal is going to cool down, the cool water is going to warm up, and they're going to meet at the same spot and stop changing. So in my experiment, they both landed at 23. So if you look, the metal changed its temperature quite a bit. It went from 100 down to 23, so that was a change of 77. It went down 77. But the water didn't change very much at all. It went from 20 degrees down to 23 degrees, or up to 23 degrees, so only a 3-degree change. If you are predicting which one has a higher specific heat, this is the giveaway right here. But let's actually keep going with the calculation so that we can see it. The last thing that we need in order to solve for the metal's specific heat, that's C, we need to know water's specific heat, and this is a very well-known quantity. It's 4.184. Not a number you have to memorize, but we do need it to solve our calculations. So now we have our data table. We can actually go and figure out what was the specific heat of the metal, and we're going to use this equation. But we have to make one more assumption before we do, and here's what we have to assume. All of the heat that was lost from the metal, so when we took that really hot metal and we put it into the water, it lost some of its heat. Heat can't be destroyed. It has to go somewhere. So we're going to make the assumption that since we were using a nice and insulated little cup, the only place it could have gone is into the water, and that's why the temperature of the water went up. So if we measure the heat that was lost by the metal, it has to be equal to the heat that was gained by the water. That's a big assumption that we're going to make, but it allows us to build our equation. Since heat added is equal to all this Cm delta T stuff, we can take Cm delta T and just call that the heat. So we're going to put that on this side. We know that the heat that was lost from the metal, everything in blue, has to be Cm delta T. And that's all the heat lost from the metal. That has to be equal to the heat gained by the water, so that's going to be the Cm delta T gained by the water. So essentially we're kind of like saying Q equals Q, except we just took the other side of the equation. All this equals all of this. Now we can start plugging in numbers that we know. So the left side is all about the metal, the right side is all about the water. So when I plug that in, I don't know the specific heat of the metal. And by the way, I've distributed my negative sign. So that's going to just stay a negative C. I do know the mass of the metal though, so that was 12. And it's a negative now because I distributed. The temperature went down 77. So I plug in a 77 since a negative is a positive. So we've got all our signs correct. On the other side of the equation, I do know the specific heat of my water, I know the mass of the water, and I know how much the temperature changed of the water. So I have all of those numbers. Now it's just a simple algebra problem. I just need to get all of my numbers on the same side, and I've solved for C. So when I multiply everything out on either side, I've simplified. I get 924C equals 627.6, just to do a little division. And I find out that the specific heat of my metal is 0.68 joules per grams degrees Celsius. Now that number might not make a lot of sense until you consider what it means. It means that it takes about 2/3 of a joule to make a single gram of this metal go up a degree. We don't really know what joules are very well yet because we don't really use that very often, but let's compare that to water. Water takes a little over 4 joules to go up for a single gram of it to go up a degree Celsius. In other words, water takes a lot of energy to change its temperature, whereas this chunk of metal does not take a lot of energy to change its temperature. You've probably noticed this if ever you're like leaning against a car in the middle of summer. A car is made out of metal. It does not take very long in the summer heat for a car to heat up to a really high temperature. But if you were to take a bucket of water and sit it out in the sun, it's going to take a really long time for that bucket of water to get hot because water can hold a lot of heat before its temperature changes. So please move on to the practice questions. Pause the screen or pause the video so that you can read the screen and answer these practice questions in the boxes on your paper. And then in the lab, I want you to consider the questions for that section as well. So please pause the video now.